In chemistry, polarity refers to a separation of electric charge leading to a molecule or its chemical groups having an electric dipole or multipole moment. Polar molecules interact through dipolar-dipole intermolecular forces and hydrogen bonds. Molecular polarity is dependent on the difference in electronegativity between atoms in a compound and the asymmetry of the compound's structure. Polarity underlies a number of physical properties including surface tension, solubility, and melting and boiling points. Background: polarity of bonds. Electrons are not always shared equally between two bonding atoms. One atom might exert more of a force on the electron cloud than the other, in which case can make a dipole-dipole intermolecular force. This pull is termed electronegativity and measures the attraction for electrons a particular atom has. The unequal sharing of electrons within a bond leads to the formation of an electric dipole, a separation of positive and negative electric charge. Partial charges are denoted as I+ and Ia. These symbols were introduced by Christopher Ingold and his wife Hilda Usherwood in 1926. Atoms with high electronegativities such as fluorine, oxygen, and nitrogen exert a greater pull on electrons than atoms with lower electronegativities. In a bond, this can lead to unequal sharing of electrons between the atoms, as electrons will be drawn closer to the atom with the higher electronegativity. Bonds can fall between one of two extremes being completely nonpolar or completely polar. A completely nonpolar bond occurs when the electronegativities are identical and therefore possess a difference of zero. A completely polar bond is more correctly called an ionic bond and occurs when the difference between electronegativities is large enough that one atom actually takes an electron from the other. The terms polar and nonpolar are usually applied to covalent bonds, that is, bonds where the polarity is not complete. To determine the polarity of a covalent bond using numerical means, the difference between the electronegativity of the atoms is taken. On the Pauling scale, if the result is less than 0.4, the bond is generally nonpolar covalent. If the result is between 0.4 and 1.7, the bond is generally polar covalent. If the result is greater than 1.7, the bond is generally considered ionic. Pauling considered that the partial ionic character of a bond is an approximate function of the difference in electronegativity between the two bonded atoms. He estimated that a difference of 1.7 corresponds to 50% ionic character, so that a greater difference corresponds to a bond which is predominantly ionic. Polarity of molecules. While the molecules can be described as polar covalent, nonpolar covalent, or ionic, this is often a relative term, with one molecule simply being more polar or more nonpolar than another. However, the following properties are typical of such molecules. A molecule is composed of one or more chemical bonds between molecular orbitals of different atoms. A molecule may be polar either as a result of polar bonds due to differences in electronegativity as described above, or as a result of an asymmetric arrangement of nonpolar covalent bonds and non-bonding pairs of electrons known as a full molecular orbital. Polar molecules. A polar molecule has a net dipole as a result of the opposing charges from polar bonds arranged asymmetrically. Water is an example of a polar molecule since it has a slight positive charge on one side and a slight negative charge on the other. The dipoles do not cancel out, resulting in a net dipole. Due to the polar nature of the water molecule itself, polar molecules are generally able to dissolve in water. Another example includes sugars, which have many polar oxygen-hydrogen groups and are overall highly polar. The hydrogen fluoride, HF, molecule is polar by virtue of polar covalent bonds and the covalent bond electrons are displaced towards the more electronegative fluorine atom. Ammonia, NH3, molecule. The three Na-H bonds have only a slight polarity. However, the molecule has two lone electrons in an orbital that points towards the fourth apex of the approximate tetrahedron. This orbital is not participating in covalent bonding. It is electron-rich, which results in a powerful dipole across the whole ammonia molecule. In the ozone, O3, molecule, the two O bonds are nonpolar. However, The distribution of other electrons is uneven since the central atom has to share electrons with two other atoms, but each of the outer atoms has to share electrons with only one other atom. The central atom is more deprived of electrons than the others. Since the molecule has a bent geometry, the result is a dipole across the whole ozone molecule. Nonpolar molecules. A molecule may be nonpolar either when there is an equal sharing of electrons between the two atoms of a diatomic molecule or because of the symmetrical arrangement of polar bonds in a more complex molecule. For example, the boron trifluoride molecule has a trigonal planar arrangement of 3 polar bonds at 120 degree. This results in no overall dipole in the molecule. Examples of household nonpolar compounds include fats, oil, and petrol gasoline. Therefore, most nonpolar molecules are water-insoluble at room temperature. However, many nonpolar organic solvents, such as turpentine, are able to dissolve polar substances. When comparing a polar and nonpolar molecule with similar molar masses, the polar molecule in general has a higher boiling point, because the dipolar-dipole interaction between polar molecules causes greater attachment. The most common form of such an interaction is the hydrogen bond, which is also known as the H-bond. In the methane molecule, the 4 Ca-H bonds are arranged tetrahedrally around the carbon atom. Each bond has polarity. However, the bonds are arranged symmetrically so there is no overall dipole in the molecule. The diatomic oxygen molecule does not have polarity in the covalent bond because of equal electronegativity, hence there is no polarity in the molecule. Hybrids, large molecules that have one end with polar groups attached and another end with nonpolar groups, are good surfactants. They can aid in the formation of stable emulsions, or blends, of water and fats. Surfactants reduce the interfacial tension between oil and water by adsorbing at the liquid-liquid interface. Predicting molecule polarity. This classification table gives a good general understanding of predicting molecular dipole of some general molecular structures. However, one should not interpret it literally. Determining the point group is a useful way to predict polarity of a molecule. In general, a molecule will not possess dipole moment, if the individual bond dipole moments of the molecule cancel each other out. This is because dipole moments are Euclidean vector quantities with magnitude and direction, and two equal vectors who oppose each other will cancel out. Any molecule with a center of inversion or a horizontal mirror plane will not possess dipole moments. Likewise, a molecule with more than one CN axis will not possess dipole moment because dipole moments cannot lie in more than one dimension. As a consequence of that constraint, all molecules with d-symmetry will, therefore, not have dipole moment because, by definition, d-point groups have two or multiple CN axes. Since C1, CS, CaHCN and CNV point groups do not have a center of inversion, horizontal mirror planes or multiple CN axis, molecules in one of those point groups will have dipole moment. See also, polar point group, bond dipole moment, solubility, colloid, detergent, dipole, covalent bond, electronegativity, dielectric, chemical bonding. Thorium monoxide has the highest known internal electric field of any molecule. References